Hi, today is May 1st. It's been a while. I wanted to do a deep dive into the Virtio-net and the Vhost-net architecture. And I'm going to do a lab demo today in the lab to show this architecture. So again, here is the oh, it's too big. Yeah, so here is the architecture. Okay, here, yes, yeah. Here is the architecture. So this whole diagram is the QMU process for the guest. So this whole thing is in the hypervisor user space, and this is a hypervisor kernel space, and the virtual machine QMU process runs as a user space process in the hypervisor. So I run a big IP virtual machine on this hypervisor, KVM hypervisor, and this is a QMU process. So the QMU process has emulated a Virtio-net PCI device, and in the guest kernel, normally it's a Virtio-net driver, and it has a virtual rim buffer. As you can see, the virtual rim buffer is mapped to the Vhost-net rim buffer that is in the hypervisor host kernel space. Okay, so for the data plane, the packet like is here, then it's going through a tap device, and the tap device is a member of a open vSwitch bridge. So the open vSwitch bridge will forward the packet out to the physical network port. And notice here, the Vhost-net do the packet forwarding in the host kernel space. Basically, it's doing a copy from user space and a copy to user space. Copy from user space is to get a packet from the guest and forward out forward it out through open vSwitch bridge and to the outside world. And the copy to user is the copy the packet from outside the world through open vSwitch bridge, through the tap, and through the host kernel to the virtual machine, the guest kernel Virtio-net driver virtual ring. Okay, so that's the whole architecture. So first I'm going to show you the guest as a big IP as a guest running in the QMU process. So this is my hypervisor. Let me log into the big IP guest. Let's list the LSPCI. So notice here there are two Ethernet controller PCI device. One is the PCI bus 3, one is PCI bus 4. So that's two Ethernet network device on the big IP. One is for management, one is for data plan. And we can show more information. So this is the PCI network PCI bus. We want to show, okay, invalid function number. Okay, so this is the two Ethernet PCI device. Notice the subsystem. This is a PCI vendor ID and then assigned from the Red Hat. So you will always see a Virtio-net PCI device showing as Red Hat Virtio-net network device. And the kernel driver in use is Virtio PCI. So this network device is the same. Okay. So this matches the Virtio-net. So this is a guest. This is a Virtio-net PCI device emulated by the QEMU process. And then in the guest kernel, we have Virtio-net driver. So since this is a big IP, we can show the driver here. ALTX. As you can see here, so the 1.1 interface is the second network interface. See, it has the PCI bus 04.0. That's for the data plane. It's a Virtio device, and the driver is okay. Device prompt. Okay. So this is the driver. Big IP use the driver. It's a Virtio driver. Yeah. So this is for the second network device. Use Virtio-net driver for data plane. And again here, Virtio-net driver. Just keep in mind the big IP Virtio-net driver is slightly different than the official Virtio-net driver that usually comes from your Linux distribution. So in your Linux distribution, say if you're running a Ubuntu or CentOS Linux guest, you will have the standard Virtio-net driver from the Linux kernel. So this diagram basically shows you the official Linux Virtio-net driver. But since my guest is big IP, this driver, Virtio-net driver, is slightly different with some customization from big IP. But basically, it's the same. Okay, so that's the guest. And then there's a host. So in the hypervisor, in the host kernel space, hypervisor kernel space, there should be Vhost-net driver running as a kernel thread for the data plane. So let's check the hypervisor, the Vhost-net. Oh, this is on big IP. So let's go to the hypervisor. So this is the hypervisor. Let's see. Noticed. So this is the QMU process. That's the QMU process for the big IP guest. It has a long argument here, but notice here there is a 3 Vhost-net process, kernel thread running for the data plane on the hypervisor. So notice that there is a 3 Vhost-net with a process ID. This 3861 process ID is the QMU process. Notice here. So when you have a guest running in the hypervisor with QMU process, the process ID, QMU process ID 3861, you can identify the Vhost-net kernel thread with the same QMU process ID. So this 3 Vhost-net kernel thread is for this QMU process. So why it has a 3 Vhost-net? Because the first this Vhost, so it's dependent on how many Q your network device has. So if you have if one network device has 2 queues, each queue will have a Vhost-net kernel thread. We can double check. So example here. So this is our big IP guest, right? Let's show. Let's go to interface. So we have 2 network interface defined here, right? Why network interface? The second network interface. So this interface is for the management. I'm using a Linux bridge for the management. So notice here the model type is Virtio, meaning it's the Virtio network device, and driver Virtio. Driver by default using Vhost. So the second network device is I'm using Open vSwitch bridge. See here it's sourced from the Open vSwitch bridge 0. And here is I define the driver detail here. And see here driver, I have 2 queues. And each the RX queue size is 1024. So you can define the queue size here in the libvirt XML template, the TX queue size here. But here is I have 2 queues. And but this network, the management network interface, I don't have the queue defined here. So by default, it's 1 queue. So in total, there's a 3 network queue here. And so on the hypervisor, we should have 3 Vhost-net kernel threads. So each queue has a Vhost-net. That's the reason we have 3 Vhost-net. Okay. So, and yeah. And also this QMU process, it's a long argument, but we only care about the netdev argument. So let's look at so the QMU I extracted out of the netdev argument here. So the netdev here is define the network device for the guest. So the netdev define the type, it's a type device with file descriptor 26, and it's using Vhost-net. So here is on. Vhost-net file descriptor is 27. Okay. And so the emulated device is Virtio-net PCI. Again, this is a MAC address, the PCI bus. So this is for the management. And this is for the data plane, big IP, a network interface. And notice here, the file descriptor here has two file descriptor because I have two queues for this network device. So it has two file descriptors. Also, Vhost is on. The Vhost file descriptor also has two because I have two queues here for the network device. And see here, it has MQ on, meaning it has multiple queue. So I have two queue here. And also here, I have the RX queue size, TX queue size defined here. So this two network device is just a reflection of what I defined here from the libvirt, right? Two queue here for the second network device. All right. So another thing we may need to look at is see this file 28, 29 file descriptor. We can actually check this file descriptor information by look at it here. Look at. So it's 28, 29. So we can cat this device file descriptor information. Please notice this 3861 is the QMU process ID. So each Linux process has a process ID, and if you want to know all the information about the process, you go to the /proc/process ID. And for file descriptor information, we have a file fd-info directory. Under the directory, it has a file descriptor ID that is associated with this QMU process. So we can look at this descriptor information. So here it says if interface vnet1. So this file descriptor ID 28 is associated with vnet1, and 28 is also 29 is also associated with this QMU process. Let's look at it again. So it's also associated with vnet1, meaning this vnet1 has two queues. We can actually check this vnet1 on the hypervisor. So this is a vnet1. Notice here it says it has a multi-queue. So it has a multi-queue labeled. That's one queue is 28, file descriptor number 28. Second queue is 29, so it has 2 queue here, so multi-queue flag is on. Here it also tells you the master is OVS system, meaning this is its master bridge is from Open vSwitch. Okay, so that's our second network interface for the peer device on the network device on the hypervisor. And then you can also see the MAC address here matches the MAC address in the big IP for the TMM data plane interface. Okay, so there is a VNet 0. That's for the management peer device, network device. So it has the file descriptor is 26, and right, so it's VNet 0. VNet 0. Okay, so this device, this is from Linux bridge. This is from Open vSwitch bridge. Just yeah, you know. Okay, as you can see here on the hypervisor, I have OVS bridge 0 here. Okay, so that's the on the hypervisor, and we showed you the relevant information. Now let's run a load test to see what's the bottleneck for this architecture. And the main bottleneck architecture is here: copy from user and copy to user. That's you copy a packet from the user space, the QMU process, from the user space to the host kernel space. And that's the bottleneck. And I can show you I can demonstrate that here later. Okay, let's run a top. So this is our QMU process. This is our Open vSwitch process. And now let me start a node test. So we are monitor the guest CPU usage from the hypervisor. Let's start a node test. Send a HTTP request to the big IP virtual server. And again, this is a Apache Bench running on DBDK with multi-thread. So it has high performance node test. Let's start it. So I have 4 logic CPU running for this load test. So it started. As you can see here, this is close to 1 gigabit per second. So RX. So I'm sending a simple HTTP request to the virtual server, and the virtual server will send a big payload to the load test. So that's why the RX is higher. It's like close to 1 gigabit per second. The TX from the load test is only 100 megabit per second, because I'm sending a small packet to the virtual server, but the virtual server sends a large chunk of data payload to the load test. That's why the difference here. And so this is the top on the hypervisor. You notice here there's a 2 Vhost kernel thread running with a 34 CPU percentage usage. And so that's the Vhost net in the hypervisor kernel space. because we have a node test running. So let's look at what's the bottleneck here for the host kernel of Vhost-net. Let's run a Linux perf command. This is the Vhost-net process ID. Top. So that's the Vhost-net for the data plane. Okay, you notice here the most the 12% CPU cycle here is consumed by the copy user generic string, which is actually invoked from copy from either full. Okay, let's copy this whole thing here. Okay, so copy user generic string. This is a like a copy from user, like here, copy from user. So the big IP are sending, big IP in the guest are sending a large chunk of data through the virtual ring in the get Virtio-net driver to the Vhost-net virtual ring, like, and then the Vhost-net do the copy from user through the tap tunnel device, through the open vSwitch bridge, and forward out to the load tester. So notice the bottleneck here is copy from user, and our Linux perf on the Vhost-net proves that copy user generic string, copy from inner full, and yeah. So I can show you the actual kernel. I can show you the where this code path coming from. So I have a Linux source. I have a Linux source code here, and driver net top. So this is a copy from get a user page. I think it's get user. Yeah. See here, get a packet from user space buffer. That's the copy from user triggered. See here the copy from inner full. So this is the from is from the user space, from the guest, the big IP guest sending a large chunk of packet and stored in from, and then this function will copy to the GSO buffer. Let's go into this function here. So it actually runs this underscore copy from inner full, right? Copy from inner full, right? Again, the diagram. tunnel tap, which the source code is driver/driver net ton.c. Actually calls the copy from user, copy the packet from here all the way, like copy from here, from the virtual ring here, and then forward by the copy the packet into the host kernel space, and in the host kernel space, OVS forward the packet out to the physical network interface. So the main bottleneck is copy from user. If you are sending large chunk of data from the guest to outside, or if you are sending a large chunk of data request through outside to the guest, that's copy to user. Here I only demonstrated the copy from user. Okay, so this is a lab. That's the actual copy from user or copy to user. Yeah, I think that's the demonstration I want to do today, and hope I explained it clear. By the way, I can show you the Open vSwitch bridge. So I have two bridges. So this is a bridge I'm using, OVS bridge 0. This is a physical interface. This is a bridge name. So this is the peer network device Vhost-net 1 on the hypervisor we showed you earlier. This is a physical interface, right? Physical interface, a tap port, on the hypervisor. Okay, yeah, thank you for watching.